In the last lecture, we had met digital electronics for the first time, at least in this course. We had taken a look at the basic set of gates, the AND, OR and NOT, and also how to construct these gates using discrete electronic components. Beyond that, we had met the NAND and the NOR and seen how they alone, singly, can act as a universal set of gates so that you can construct every digital circuit, every Boolean circuit using just the NAND gate or the NOR gate. We have also met some basic rules of Boolean algebra and seen some very simple Boolean circuits in action. What we are going to do today is continue on that theme. What we need to learn is a way in which we could simplify Boolean functions starting either from the description or from the truth table so that we can implement them more efficiently. We will first see how we can do this by appealing to the laws of Boolean algebra that we had already learned, and then we will go on to talk about a more efficient graphical method called the Karnaugh map method. So first, the approach using good old Boolean algebra. Let us first quickly recapitulate some of the Boolean algebra rules that we had learned about in the last lecture. We had seen that if you OR A with 1 of course standing for true, you always get 1. If you OR A with 0, you get A. Now, while A plus 1 equal to 1 looks like a crazy equation if you were to interpret the plus as ordinary addition, A plus 0 equal to A does make perfect sense. Let me warn you, though, that you should get into the habit of thinking of plus as OR and dot as AND when you're doing Boolean algebra, rather than refer to them as plus or dot, because that way you might confuse yourselves with ordinary algebraic expressions. Now, A dot 1, which is A and 1, is always A. A and 0 is 0. Now, the next set of Boolean relations that we had learned involve taking the variable with itself or its complement. A and A or A are both A. That is, these expressions are high only if A is high and low when A is low. A and A bar, well, something and not that thing at the same time is impossible, and as a result, A and A bar is always 0 or false. A or A bar, on the other hand, is always true because one of the other will always occur. Now, the final law of Boolean algebra that I am going to refer to is not one which we had talked about in the last lecture, and it's a rather unusual law in the sense that it's rather difficult to prove this law using the previous basic postulates, if I may call them, of Boolean algebra. But it's rather easy to understand, and let me just try to explain to you why this is true. The law says A or A bar and B is the same as A or B. Now, why is this true? Well, if A is high, then A or A bar and B is high automatically. So, the truth of the statement is automatically established when A is true. So, what if A is false? If A is false, then A bar of course is true, and A or A bar and B basically becomes 0 or 1 and B. So it just becomes B. So this expression is low only when both A and B are low, because if A is high, the expression is high anyway. If A is low, then the expression is the same as B, which is low of course when B is low, and is high otherwise. So that exactly is what A or B is. Low only when A and B are low, false only when A and B are false, both of them, and true otherwise. So this establishes the truth of this particular Boolean identity. And you will see that this Boolean identity is actually quite useful in reducing complicated Boolean expressions. So now that we have these under our belt, let us go ahead and try to simplify some complicated or maybe not so complicated Boolean expressions. We are after all doing this primarily for practice, so the expressions that we will start from will not really be very complicated, but we are going to show you how to go ahead and simplify even more complicated expressions soon. The first example we will talk about takes a somewhat real life problem and tries to convert that to a Boolean expression. Imagine a situation where there are only 3 people voting. So they can vote true or false or high and low or 1 and 0, indicating they support a motion or do not support a motion. And the motion is carried if a majority of them votes in favor. That is, at least 2 or more of the people have to agree. So let us first convert this into a truth table where A, B and C indicates the votes 0 or 1 which each person has given, and Y indicates the result, which will be high only if a majority of the inputs is high and low if a majority of the inputs is low. Now once again let me remind you that because there are 3 inputs here, there are 8 possible input combinations, and in order to write them in order and not miss out on any one of them, we will follow the standard protocol of using the numbers 0, 1, 2, 3 right up to 7 and just use the binary equivalence 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1 and so on. So here we have this table which gives you the results of all the 8 possible combinations. Of course 0, 0, 0, nobody has voted in favor, the result is 0. 0, 0, 1, only one person has voted in favor, that's also 0. The first time we made a 1 is for 0, 1, 1, 2 people have voted in favor, 1 hasn't. That's a majority in favor. 1, 0, 0, only one person has voted in favor, still 0. 1, 0, 1 is 1, 1, 1, 0 is 1, 1, 1, 1, everybody has voted in favor, of course, is a yes. So let us now first try to write down this expression in basic Boolean form, and then we will try to simplify that. So Y is given by the following expression. Now this is something that you can immediately read off from the truth table. But let me just put this in plain English first. When is Y high or 1? Well, if you look at the rows here which has a 1, this one is saying when A is low but B and C are high. So this is the expression which is high only if A is low, that is A bar is high, and B is high and C is high. So of course this line, if this were the only non-zero one in the truth table, that is for the result, then Y would have been exactly A bar B C, which is high when and only when A is low, B and C are both high. On the other hand, our expression is high also when we have 1, 0, 1, which is A is high, B is low, C is high. That means A, B bar and C are all high together. So Y is high either when you have A bar B C being high, or when A, B bar C is high. But that of course does not complete the whole thing. You also have this line which is A, B and C is low, so you have C bar. And finally you have this line where all 3 are high, which is high only when A, B and C are each high. So this is our beginning form for the Boolean expression. Not the simplest possible form, but a form which definitely works And all we have done is taken all the rows in the truth table which has 1, essentially written down a term which will be 1 if and only if this combination occurs, and then ORed them all together to ensure that the result will be 1 whenever any one of these, A bar BC, AB bar C, ABC bar or ABC is high. So as I said, this is our beginning form, but not the most simple form. So how can you simplify this? One thing immediately comes to mind. If you look at this term and this term, you see AB is common. So you could immediately do something like this. A bar BC plus AB bar C plus AB times C plus C bar. Now this is something which I did not mention in my set of rules of Boolean algebra, but I definitely should have done that. Our rules of Boolean algebra should also include things like distributivity of the AND and the OR. That is, X and Y or Z is the same as X and Y or X and Z. This is something you can easily verify from the truth tables, or you can try to argue this out using basic logic as to why that should be true. But the upshot of it is this formula, which works also for multiplication and addition and looks very much like elementary mathematics formula, is actually valid also for Boolean algebra. And that is exactly what we have used here, only that we have used it in reverse. That is, we have used it to combine two terms. But now what kicks in is this result, C plus C bar. What is that? We know this is always true. Okay, although I told you that you should not think in terms of plus and dot, but rather in terms of OR and, while speaking I might very well lapse into plus or dot simply because that's sometimes more convenient, and that's what you can see in front of you. As long as you understand that when I say plus here, I mean OR, and when I say dot, I mean AND, rather than addition or multiplication, you will be fine. But now you have AB and 1, and that of course is just AB. So our first round of simplification simply looks like this. But this is definitely not the most simple form for this particular expression. Now you might wonder about one thing. Here we combine these two terms together and got AB out of it. However, we could have easily combined this one not with this but with this and taken A and C common. One more important Boolean algebra rule which I may have forgotten to mention. X and Y is the same as Y and X. And for OR also the same thing works. X or Y is the same as Y or X. This may seem rather obvious, but these are important algebraic rules that we are using here. So I can write AB bar C also as ACB bar. I can write ABC also as ACB, and I can combine them together to get AC times B plus B bar. And that will give me AC times 1, and that is AC. So instead of simplifying this term, I could sacrifice this and simplify this one. And you can easily see I could also simplify this one by just combining ABC with this to get A plus A bar BC, and that will give you BC according to the same set of rules that we have just applied here. So the only trouble is we have only one ABC. So I can simplify only one of these terms, not all of them. But can't I? And this is where Boolean algebra's major difference with ordinary algebra kicks in. What you can do is can write ABC as ABC plus ABC plus ABC. Remember, A plus A or A is actually A. And that works for more than one A as well. So I can just repeat this as many times as I want. And now, notice that I can use this ABC, combine it with this one to get BC. Combine this ABC with this one to get AC. And combine this ABC with this one, as I had done already here, to get AB. So, if I were to write it out in full, I will be doing A bar plus A PC plus AC times B plus B bar plus AB times C plus C bar, and that will reduce to BC plus CA plus AB. This is the simplest form which the three-voter majority voting function takes. Now here, you might have several questions, or at least several procedural questions. How did I know that I have to take ABC thrice? I argued that here, but given a more complicated expression, how can I figure out that that is exactly what I have to do? Or now that I have simplified this, how am I so sure that this is the simplest that I can go? Why can't I try anything else? Some complicated combination of the rules that we had written down before to get to this, or something simpler. Well, if you were to just use Boolean algebra rules and try to simplify a complicated expression, sometimes you have to deal with much more complicated expressions than this one. These questions would really become rather problematic, because figuring out the best way to simplify the expression may not be so obvious. And after you have simplified the expression, whether you have really got to the simplest possible form or whether you could do something more after that may not really be obvious. As you will see, the other method that we are going to talk about soon is actually going to help you solve both of these problems. You will be able to figure out what to do and also figure out when you have just reached the most efficient form, or at least one of the simplest possible forms. But before we go and describe that method, let me at least show you one more example of using Boolean algebra to simplify expressions with one more Boolean expression to begin with. For our second example, we have this truth table here. Don't ask me where I got this truth table from, because frankly I just wrote down an arbitrary column of zeros and ones here for the result. But I can see that there are 3 ones, and when you just look at those ones and only those ones, you can immediately write down the first form for this. After all, this one will be A bar, B, C bar. This one will be non-zero 1 only if you have A bar, B, C, and the final one will be A, B, C bar. And when you OR all of them together, you get a Boolean expression which will be high only if though any one of those 3 combinations occur. So you have got this Boolean expression to begin with. Now how can we simplify this? There can of course be many approaches, but you can immediately see the first 2 terms can be combined together to give A bar B, C or C bar, ORed with ABC bar. And this, as we have already seen in the last example, simplifies very simply to A bar B, and then you have A, B, C bar. But the simplification does not end here. You can take B as a common factor out of both of them, or common logical expression which you are going to AND with the rest, and you are going to end up with A bar or AC bar. This is an expression where we can use our final Boolean algebra law, that is, just to remind you, A plus A bar B is A plus B. Here you have A bar plus AC bar, but the same rule applies. This is going to be B times A bar plus C bar. So it's A bar B or BC bar. Now both of these could be taken as the final simplified expression. Whether you want an AND at the end or an OR at the end is a matter of taste or sometimes of practical implementability. In the last lecture we talked about implementing a circuit only with NAND or NOR gates. If you want to implement a circuit with only NAND gates, It's actually better if you have an expression which ends with an or, so this will be more useful. If you want to implement it with NOR gates only, this would be more useful to begin with. However, as you can see, these two are exactly the same expressions. Once again, the same questions may arise. Why am I so sure that this is the only way to do it? Or how did I even think about this way? Or the other question, how am I so sure that I've really got the final answer? So we will have to see that. And so as promised, we will talk about a method that will make both of these problems go away. And at a glance, literally at a glance, you should be able to see the easiest way to simplify the expression. Also, you should be able to convince yourself that what you have obtained is the simplest form. Or, as you can see in this case, one of the simplest forms. Because both of the final results, the last two lines here, are both equally good as simplest possible forms. Let us now take a look at the Karnaugh map method. The method that we have been promising will allow us to simplify Boolean expressions visually, literally at a glance. So to understand this method, which can be a bit difficult if you are meeting this for the first time, let us start with the simplest possibility. We have only two input variables A and B. So with two variables, of course, you can have only four possible combinations: 0, 0, 0, 1, 1, 0 and 1, 1. And to represent those four possible input combinations, the Karnaugh map in this case consists of four boxes. Now, as I've drawn on the left, these four boxes are labeled by which variable they quote-unquote belong to. But the belonging is not exclusive. The first two boxes here, as I've labeled, this one and this one, belong to the variable A. Now the last two do not belong to B. That would be wrong, because the last two would actually belong to A bar. They are completely out of A. Actually, what we do is the second and third box here belong to B. Now, of course, this is a convention. I could have had the second and third belong to A, the first and the third belong to B, or something of that kind. But this is sort of a universal convention that is followed. Now, that means that I am going to put the result of A high, B low in the very first box, simply because the first box belongs to A and does not belong to B, so to speak. So, the input combination A high, B low, or simply 1, 0 is going to be written in this box. The output for that input combination, I mean. Similarly, the output for the input combination A and B both high, 1, 1 will go here. A low, B high, 0, 1 will go here. A low, B low will go here. If you were to convert these numbers 1, 0, 1, 1, 0, 1, 0, 0 to simply decimal numbers, the kind that we can talk about more simply, you end up with these numbers 2, 3, 1 and 0. So, from right to left, these numbers tend to increase at the beginning, but you have this switch. It goes 0, 1, then 2 jumps a place, then comes back to 3. Now there's no mystery about that. These are simply the combinations which are high or low depending on which variable the box belongs to or does not belong to. So this is the basic setup. Both of this, or simply a row of four boxes without the 1, 0, 1, 1, 0, 1 or 2, 3, 1, 0 markings, they can be our starting point. All you have to be sure about is which boxes belong to which variable. And so, usually we would just start with four boxes with A's marked and B's marked without these numbers in the boxes. These numbers in the boxes actually are pretty useful, especially when you're doing problems with more than two variables, 3 or 4. We will see how to handle those soon. There, keeping track of which input combination goes where becomes much easier if you just had these numerical values. And as you will soon see, the pattern is not that difficult to memorize or at least recover every time, so that it would be rather easy to fill up these boxes with the corresponding outputs. So let's now see how to actually use this. So first, an example of filling up the boxes with the outputs. Look at the truth table on the left here. This, of course, is a truth table for a rather well-known Boolean expression. It is low only when both inputs are high and high otherwise. If you think of its complement, that would be high only when both inputs are high and low otherwise, and that is definitely very well known. That would be the AND gate. So this really is a truth table which talks about the NAND gate. AB whole bar or A bar plus B bar. Now if you were to fill up the boxes in the Karnaugh map here, you would have to either fill up the 3 ones first or the 1 0 first. Usually what I do is take a look at whichever one of the two are lower in number, fill those boxes up first, although feel free to use whatever order you want. Now I know that there is only 1 0 and that will go in the 1 1 box. I know the 1 1 box is the second from the left, either because I can see 1 1 is written here, or if I had forgotten that but rather remembered this one, 2 3 1 0, I would just remember that the binary number 1 1 is equivalent to the decimal 3, and the 3 is where you will put in the 0. Or, well, you don't have to mark the boxes with input numbers anyway. All you could say is this output is low only when both inputs are high. That means in a box which belongs to both A and B, and that will definitely go here, because that is the box which is common between A and B's ownership. Of course, once I have filled in the 0, I am free to fill in the 1s elsewhere. So all the other 3 boxes get filled with 1s. So this is our beginning step. You start with a truth table or sometimes just a statement of the problem, and once you get used to this, you can actually directly fill up the boxes starting from the statement of the problem itself, but it always helps perhaps and saves confusion if you have a truth table to begin with. And you write down the outputs in the appropriate boxes. The next question is, how does this really help in simplifying the expression? For 2 variables, of course, you don't really need the Karnaugh map. It's pretty easy to simplify the expressions just by looking at them. There are only so many possible Boolean functions in 2 variables, and you can just perhaps recognize all of them at a glance. Like, you should have been able to recognize that this is a NAND gate truth table just by looking at it. But let me see how we can actually simplify the whole process. And as I've just said, this is a warm-up. So you will not really be using this method for 2 variables that much. But to learn the ropes, we are going to try to do this for 2 variables first. To begin with, let us take a look at some very simple Boolean expressions and their corresponding Karnaugh map representations. Indeed, the simplest Karnaugh map representations have not been drawn here. A Karnaugh map with all 4 boxes filled with zeros definitely represents the 0 function or the false function, a function whose output is always false or low or 0. Similarly, a Karnaugh map with all 4 boxes filled with 1s would stand for the true function, a function whose constant output for all possible inputs is true or 1 or high. Now, what about the variables themselves? A alone would of course give rise to a Karnaugh map where the A boxes are filled with 1 and the not A boxes are filled with 0. So that's what you have on the left here. You can see the 2 1s form a block, a 2 block rectangle of contagious ones. What about A bar? Well, there the ones will be sitting on the boxes which do not belong to A, that is, these two boxes, and zeros here. And once again you will notice that they form a rectangular block of two elements. What about B? Well, 1, 1, block of two elements again. Well, B bar, that's where we again get two ones, but they are apparently not next to each other, so that they don't form a contiguous block. But you can actually easily make this into a contiguous block if you imagine that these two ends of the Karnaugh map are actually joined together. In mathematical terms, we would say you identify the left edge with the right edge. Or, in more geometrical terms, I would say just roll up the Karnaugh map so that the left edge and right edge match, so that 1 and 1 come together. So basically here we see the simplest possible functions essentially are represented by two blocks which are contiguous, provided you do the identification that the left edge and the right edge of the Karnaugh map are actually rolled up together. On the other hand, consider this particular Karnaugh map, which has only one single one sitting there, so you can't have a contiguous set of 2 or 4 as the case with the constant true function was. The best you can have is, of course, a contiguous set of only one element. Now what would the corresponding Boolean expression be? Now that's straightforward. This box belongs to A but does not belong to B. So this is really A, B bar. So that is a simple way in which you can recognize which variables go in and which don't. If I were to sort of repeat this is rather easy, although you can see it's A to begin with. But let's just say we didn't know that from the beginning. We would say this is high whenever A is high, as you can see. Both of them are in A, so this will definitely be in A. But one part of this block is in B, one part of this is out of B. So this is really neither B nor B bar. So B will simply not appear. So we will just be left with an A. Now that of course is a rather trivial thing to say, but we will see that thinking like this actually helps you in more complicated situations, like when you are dealing with 3 or 4 variables. Let us now try to use whatever we have learned here to simplify the truth table that we began with, the NAND gate truth table, and the corresponding Karnaugh map which we have already drawn a while ago. Let us now make use of what we have just learned over the last few minutes and try to simplify the Boolean expression for the Karnaugh map that we had constructed a while ago. We of course know the answer. This is a NAND gate, so we know that the result will be either A, B's complement, that is the complement of A and B, or the other way of putting it, A bar or B bar. But let us try using the Karnaugh map method to figure that out. Now there are 3 ones in the Karnaugh map. We will have to focus on them and look at the largest possible blocks that we can make. I can immediately identify one block of the 2 ones here and another block which is sitting by itself. Now let's take a look at this one first. This one corresponds to a simple Boolean expression which we had just seen a while ago, but let's just pretend we have forgotten all about that. But how can we convert this block into a Boolean expression? That's simple. You see that both the elements of this block is outside A, so this will definitely give you A bar. But part of the block is in B, part of it is out of B, which tells us that B will not contribute to the expression at all. So the simplified expression for this block is A bar. But that's not all. You also have this one term to play with. And we have already seen this just a while ago. But let me just remind you once again, if you've forgotten in a few minutes what went on before. This block is inside A definitely and is definitely outside B. So this actually contributes AB bar. not the answer we were looking for. The answer we were looking for was A bar plus B bar, but this is, well, a step in the way, not the best thing to do. Of course, I could use our identity, A plus A bar B is A plus B, and use that to simplify this further. But let's try to see how you would do this entirely using the Karnaugh map. And the answer here is, as you have just seen a while ago, bigger blocks give you simpler expressions. 4 blocks of 1 gives you just the constant function 1. 2 blocks of 1 gives you either A or A bar or B bar. A singlet block gives you AB bar or some other combination of 2 Boolean variables. So our aim should be to try to get the biggest possible blocks. Now, I have managed to get 2 blocks here. By the way, the size of these blocks has to be 2 or 4 or 1, powers of 2. The reason for that should be more or less obvious. But now, I can see a 2 block in the picture, and I can see this sitting all alone, but we have just seen that you can wrap up the Karnaugh map so that the edges come together. So strictly speaking, what I should really look at to try to get the simplest possible Boolean expression, the largest possible blocks, would be this. This is one block as we have seen before, but this one and this one actually form a 2 block. We have already seen this before when we talked about B bar, and this really is B bar again, that particular block. But this is something to remember when you are actually simplifying Karnaugh map expressions. Try to get the biggest possible block, and if necessary, use the fact that the edges are identified. So this block, this one and this one together form one block, which we already know is B bar. So now we have a blue block, or a block marked out in blue. That's A bar, as we have already seen. And the block made out of these two, well, 2 elements, both of which are outside V, that's your B bar. So this is how the Karnaugh map helps in simplifying the expression. Doesn't look like much, at least with 2 variables. After all, with 2 variables, there isn't much to simplify. But as you will soon see, when we go to 3 or 4 variables, this method really becomes very, very useful. Just identify 1 blocks, 2 blocks, 4 blocks, 8 blocks, as the case may be. They have to be contiguous rectangular blocks. Try to get the biggest ones of them, and try to also do with as few of them as possible. I will summarize these rules once again later, but this is basically how you simplify a Boolean expression using the Karnaugh map technique. The 3-variable Karnaugh map is a simple generalization of what we have seen with 2 variables. With 3 variables, there are 8 possible input combinations, and we indicate them with 8 boxes, but now in 2 rows with 4 boxes each. Now, as before, the first 2 columns belong to A. The second and third columns, again as before, belong to B. But now the first row is given to C. Once again, this particular assignment of the first 2 columns to A, the second and third to B, and so on, is a convention. But this is a convention which almost everybody follows. So it would be good if you also followed the same convention. Now, what do any one of these boxes represent? For example, if you take a look at this one, this box is completely out of A, right? It's not in a column which belongs to A. It is in a column which belongs to B, and it's in the row which belongs to C. So this actually stands for a situation where A is low, B and C are high, which has been indicated by 0, 1, 1 here. Just to sort of make sure that we have understood the whole thing, let's take a look at another one. This one is in A, out of B, out of C. So 1, 0, 0. On the right, you see the same Karnaugh map inputs indicated, but this time indicated using the decimal equivalence of these numbers. Now, the rule is here, you will go 0, 1 2, 3. These are of course nothing but the decimal equivalents of these numbers. But then you will skip a column, come to 4, 5 and then 6, 7. Remember we had the same thing before. With 2 inputs you had 0, 1, then 3, then 2. So 0, 1, skip a box, go to 2, then come back to 3. The same sort of thing here. When you're going up, there's nothing to skip. 0, 1, then 2, 3, then skip a column, go to 4, 5, come back to 6, 7. Remembering that actually helps you to build up Karnaugh maps in more complicated situations quite quickly. But anyway, you don't have to remember any of this. Just remember the assignments. This box once again is for something which is in A, in B and in C. So 1, 1, 1 in binary here or 7 in decimal. To see how the Karnaugh map method works, let us take a look at this particular truth table that you see on the left on your screen now. I've just written down some arbitrary output combinations of zeros and ones. But now I have exactly equal number of zeros and ones in my output. So it doesn't matter whether you fill up the zeros first or the ones first. Both will require you to fill up 4 boxes with the appropriate 1 or 0 and fill up the rest with the other symbol. Now let me just illustrate how you would go about doing it. This is 0, 0, 1. That's the binary, but the decimal one is this is 0, this is 1, 2, 3, 4, 5, 6 and 7. Just the corresponding decimal numbers. Remember, that's exactly how we have been filling up the rows with inputs so that we don't miss out on any one of them. But now, input of 1 gives you 1, input of 5, 6 and 7 gives you 1. So, if you remember the rule, 0, 1, 2, 3, 4, 5, 6, 7, you can immediately fill in the ones. You get a 1 in output for the input combination 1, which is 0, 0, 1 of course. For the input combination 5, 1, 0, 1. For the input combination 6, 1, 1, 0. For the input combination 7, 1, 1, 1. Of course, the rest gets zeros. Once you get used to it, you can fill this up pretty fast. So now that the Karnaugh map is filled up for us, we will now ask ourselves what kind of blocks we can make here. We want the largest possible blocks. Okay, not blocks of any size, but they have to be contiguous rectangular blocks. Squares are counted as rectangles for this purpose. And then you have to make sure that you're doing the least number of such blocks, because each block will give rise to one term in the expression. And you want to make each block as big as possible, because bigger blocks, as you have seen, give simpler individual expressions. So I can immediately see a 1 block here. I can see another 2 block here. And the one which we don't really have sitting here. We have only a 1 block sitting here, but as we have already learned, you would be better off treating the Karnaugh map as if it has been rolled up like this, so that these 2 ones are really contiguous and they form a 2 block. You should be able to convince yourself just by looking at this that this is the best we can do. But now that we have managed to do this, writing down the corresponding Boolean expression becomes easy. This one is simply in both A and B, so this will be AB. This one is in A, inside and outside B, so no B in the expression, and completely in C. So this is AC. What about these 2? Well, one is in A, one is outside A, so no A here. Both are outside B, so that's B bar. Both are inside C, so that is B bar C. So the AB plus AC plus B bar C, that's the simplified Boolean expression corresponding to this truth table. And note that here, identifying that we have actually gotten to the simplest form is easy. You can see that there are no further blocks to be really found out. Of course, you can add more blocks, like you can add this one or this one, but these we have already taken in, and so we don't really need to add them all over again. I know I run the risk of sounding like a stuck record, but this is perhaps the right time to summarize all that we have said so far about using the Karnaugh map method. So, you create your Karnaugh map, and then when you want to analyze the results, what you do is capture all the ones in the Karnaugh map in contiguous rectangular blocks. As always, rectangles can also include squares. Now, each of these blocks should be of size 1. I left out the 1, but that's also a possibility. 2, 4, 8, 16, and so on, of course, depending on how many variables you really have. Now, in case you're wondering why it should be a power of 2, let me just explain with a particular example. Suppose you were considering the expression AB bar in a scenario where you have 3 variables A, B, and C. Now, when you are saying that this expression is AB bar, that means the value of A is fixed for all the blocks involved. A has to be 1, and so is the value of B, which has to be 0. So all the blocks that you are going to talk about, all the squares in the Karnaugh cycle, they actually correspond to A equal to 1, B equal to 0 now, and the only choice you have is in the value of C. C now, of course, can take 2 values, either 1 or 0. So you have exactly 2 squares which make up this particular block for AB bar. Looking ahead a bit, suppose you had 4 variables, A, B, C, and D, and you were still talking about AB bar. Once again, A has to be 1, B has to be 0, but now you have 2 choices for the value of C, 2 choices for the value of D. So overall, 2 times 2, 4 squares will all be high or all have a 1 in it when you're talking of AB bar. So you can easily see that this argument can be extended, and this tells you why you can have blocks with size 1, 2, 4, 8, powers of 2. Okay. The rule is use the largest possible blocks and use as few of them as possible. Remember, the edges are identified, especially long edges which are 4 units long. They have to be thought of as being rolled together. Now, this is also very important. If reusing one or more ones allows you to achieve largest possible blocks, I wrote the last point, but I put in the edges are identified after that, so I'm talking really of the point before that. Largest possible blocks. So if reusing one or more of these ones, squares which have ones in them, allows you to achieve the largest blocks, reuse them by all means. This is very important, and what this corresponds to is basically the same thing that we did when we repeated ABC thrice in the majority voting box example. Instead of taking it once, we used it 3 times, secure in the knowledge that ABC plus ABC plus ABC is ABC, and you can use one ABC with each of the other terms to simplify that. Basically, in the Karnaugh map picture of that, the square which corresponds to ABC, all 3 high, would actually be taken with 3 other squares to produce 3 rectangular 2 blocks and simplify the problem. I would urge you to check that by using the Karnaugh map method for the majority voting box example and see that in order to simplify this as much as possible, you have to reuse the ABC square in 3 different 2 blocks. So what we did using Boolean algebra earlier, Karnaugh map makes it sort of obvious visually. You can see that that square can be put in conjunction with 3 other squares to form 3 distinct 2 blocks, making the repeating of that square sort of obvious. But be careful not to use more than you need though. The important thing is you may repeat a square, but if all squares have already been accounted for, all squares with ones in them have already been accounted for, you do not need to go further. That way you will only be adding extra terms which you don't really want. And once you have done that, you can immediately read off the optimal Boolean function for all of this. So after the warm-up exercise with only 2 variables and a slightly non-trivial case with 3 variables, we are now primed up to discuss the 4 variable case. Now using ordinary Karnaugh maps, that's the largest number of variables you can handle, simply because in 2 dimensions that's the best thing you can draw. There are ways to extend this method beyond 4 variables, but we are not going to go into those because frankly we will not need much more than 4 variables ever, at least in our course, and also because that would take us too far afield and we don't really have that much time to spend on this topic. So let us quickly talk about the 4 variable scenario. You have 4 Boolean variables, A, B, C and D. 16 possible input combinations. So you have 16 squares which you put in a 4x4 grid. The first 2 columns, as always, stand for A. Second and third columns stand for B. Now the change from the 3 variable scenario is C now straddles 2 rows, the first and the second, and you repeat with the rows what you did with the columns a while ago. D, the 4th variable, straddles the second and the third rows. Now, I will urge you to verify for yourselves that the assignments that I have put to the input combinations, like say 0, 1, 1, 0 here, makes sense. Let me just verify that one for you. This is outside A, so A gets a 0. In B, so B gets a 1. In C, so C gets a 1. Out of D, so D gets a 0. So you have 0, 1, 1, 0 there, which of course is binary and its decimal equivalent is the number 6. So this square in the decimal labeling version is written 6. Now you can complete the labeling of all these squares. These labels, let me remind you, stand for the input combinations. And once again, let me point out that there is a very simple way of remembering this. Here when you go up, you go 0, 1 and then skip a row, go to 2, come back to 3. 0, 1, 2, 3. Next, 4, 5, skip a row 6, come back to 7. Then you skip a column. So every third column gets skipped. You get 8, 9. This is wrong. So I forgot the skip rule. So this is 8, 9, 10, 11. And then you come back to this column. You get 12, 13. Again, this is wrong. 14, 15. Just to verify, this 15 here corresponds to the binary 1, 1, 1, 1. So the rule is simple. You go up the row. When you cross 2, you jump 1 row, jump 1 column, put 2 there, then come back. Repeat with the second column, 4, 5, jump 6, 7. Then jump a column, 8, 9, 10, 11, then 12, 13, 14, 15. Now once again, you don't really have to memorize this. You can actually recognize the pattern and use it to reconstruct these numbers. You don't even need the numbers. You can just go by whether a term box, that is a small box, stands in A, out of A, in B, out of B, and use that to decide which particular square corresponds to which particular input combination. As an example of an application of this 4 variable Karnaugh map, we will talk about something which was very familiar to all of us as we grew up in the 1970s, 80s and so on. This was a 7-segment display. I'm pretty sure even today's students have seen the 7-segment display in places. Although with advances in display technology, the use of these things, which used to be all over the place at one time, have definitely gone down. In the 7-segment display, you basically display the 10 digits 0, 1, 2, 3 up to 9 using 7 segments, typically LEDs which would light up or LCDs which would change color or whatever. On the left here we are showing all the 7 segments with their names. The names are easy to remember. They go clockwise round starting from the top A, B, C, D, E, F, and the middle bar gets the name G. And these are of course pretty familiar. It should be pretty familiar. I hope nobody here is so young not to have seen this. Of the various digits 0, 1, 2, 3, etc. with certain of the 7 segments on for each one of the digits. For example, for 0, 6 of the 7 segments are on, only G is off. 8 of course have all the 7 segments on. For 1, for example, only B and C are on, everything else is off. For 2, A, B, G, E and D are on, and so on. So, if you want to build a circuit, Boolean circuit, which is going to implement the 7-segment display, what you need is to figure out Boolean expressions for each of the 7 variables, output variables here. So, small a, for example, is the output variable. It will tell me when the segment A is going to light up. Of course, that's going to happen when the input is 0, 2, 3, 5, 6, 7, 8 and 9. And not happen when the input decimal number is 1 or 4. Now, of course, in a digital circuit, the input is not given using decimal numbers. The input is given using binary numbers. Since we are talking of 10 digits here, we need to be able to accommodate 10 possible input combinations. So 3 Boolean variables will not do because they will give you only 8. So we have to go for 4 Boolean variables. Here we meet for the first time a new feature which is actually very important, and we have not talked about this so far. This happens to be so-called don't care inputs or don't care conditions. Notice that because we are going to use 4 Boolean digits or 4 bits to encode the input here, we actually have 16 possible input combinations. In decimal, we have only 10 digits. So, the first 10 of these input combinations, those corresponding to the decimal numbers 0 through 9, are actually ones which are relevant to us. The inputs 10, 11, 12, 13, 14 and 15 ending at 1, 1, 1, 1 are not really relevant for this particular problem. They are inputs for which we don't really care what the output is, simply because our circuitry will not give us those inputs in the application that we are thinking about. Now the question is, what should the output be for these irrelevant inputs? Now one might be tempted to say the output should be 0. Or you might be tempted to say the output should always be 1 for such don't care cases. Remember, a Boolean circuit implements a Boolean function, which means for each and every input combination, the Boolean function has to have an output. We may not care what the output is, but the output has to be there. And the design of the circuit will depend on that. Now it so happens that making a flat statement like all the don't care inputs should correspond to 0 output or to a 1 output actually is not a very good idea. You will be able to simplify your circuits a lot more, way more in fact, if you actually allow yourself the flexibility of choosing the don't care outputs to be either 0 or 1 depending on whichever one allows you to simplify the function the most. Now, using ordinary Boolean algebra, this becomes a huge pain because deciding which particular bunch of output combinations actually help in simplifying the thing the most is very, very difficult that way. As we will soon see, the Karnaugh map technique makes it very, very easy to decide whether I should assign a 0 or a 1 to a particular don't care input combination as output. So let me just illustrate this by showing you how to decide what the Boolean functions will be for a couple of these 7 segments. Of course, you should be able to figure out what will the case be for the other segments just by following the same technique. Let us now construct the Karnaugh map for the segment A in the 7 segment display. We could of course have written down the truth table first. For example, 0, 0, 0, 0, which corresponds to the digit 0, would have A equal to 1 because A is lighted for 0. 0, 0, 0, 1 would have A equal to 0 and so on. But given the fact that we can see in which of these digits the segment is on and in which ones they are off, it is pretty easy to actually construct the Karnaugh map directly even without going through writing down the truth table first. In fact, as we have just said, only for 2 of the digits, 1 and 4, do you really have a 0 in the Karnaugh map. This of course is for the relevant inputs, 0 through 9. So in order to construct the Karnaugh map, all you have to do is first put in the 2 zeros in the right places. Remember the count, this is 0, 1, 2, then back to 3 and so on. 4, 5, 6, back to 7 and so on. 8, 9, 10, back to 11. Then you come back along the columns and now you have 12, 13, 15, 14. Sorry, 12, 13, 14 and 15. Now, first of all, what we can do is cross out all these 6 blocks. Now this crossing simply indicates that these are don't care inputs. We don't really care whether the output is 0 and 1 for our application. We will definitely care a lot as far as simplification of the expression goes. So we just fill up square number 1 and square number 4 with the zeros. The rest of the relevant squares get filled up with 1s and these don't care input combinations get filled up with crosses. Now we get to the job of simplifying that expression as much as possible by exploiting the fact that the don't care inputs correspond to outputs which can be either 0 or 1. It doesn't matter which one. Now note that we already have, okay, I've just drawn it again on the right hand side. I'm leaving these blocks empty because now what we have to do is decide what to put in there so that this simplifies as much as possible. Now we already have a 4 block, which is nice. Bigger blocks are simpler. But note that we could easily have an 8 block by extending the whole thing. Right? Okay, now that we have 2 1s here, by converting the don't cares to 1s, we actually can see a nice rectangular 4 block, which is also great, but I could easily make this into an 8 block by just making these 2 don't cares also 1s. So let me just write down the corresponding expressions for this particular 8 block. This is in C. Completely, and you can easily see that none of the other variables will contribute because this is in A out of A, in B out of B, in D out of D and so on. So this 8 block is simply C. This 8 block equally easily is A. Of course that doesn't complete the whole thing. This 1 block, you will not keep it as a singlet, you will actually reuse these 3 to make this into a 4 block. 4 is the largest you can do. You could have put 6 of them together, but 6 doesn't count. You need powers of 2. So this is a 4 block. Now what is this 4 block? It's completely in D and completely in B. And moment sort will show you that A or C will not count here. So this is just BD. Now this still leaves this one solitary thing out, but realizing that you can roll up the long sides, in fact both the long sides here, means that these 4 together actually go into a 4 block. And these 4 together correspond to a block which is in A out of A, so no A's, in C out of C's, no C's, but completely out of D, so D bar, and completely out of B, B bar. So this is a B bar, D bar. So considering the fact that you can give the don't care inputs any output value, which will help you simplify the expression, you can get to a rather simple expression for the segment A. In this case, of course, the best thing to do would have been to make all the don't cares ones. That may not always be the case. Sometimes it may be beneficial to make some of them ones, some others zeros. But what will be the most beneficial choice is something you can easily see directly in front of your eyes by using the Karnaugh map technique. Just for the sake of practice, let me show you how to do another one. This time we are going to take a look at the segment labeled G, that is the middle line here. So as you can see from these pictures, 0, 1 and 7 have a low value for this particular output which drives the segment G. The rest 2, 3, 4, 5, 6, 8 and 9 all have a high value for G. So let me first fill up the Karnaugh map. Remember once again the number of zeros is less. So 0, 1 and 7. These are the 3 positions I am going to fill up with zeros. But before we even do that, let me fill up the don't care positions first. These are the 6 don't care positions for this particular problem. The zeros go in positions number 0, 1 and 7. Remember this is 0, 1, 2, 3, 4, 5, 6, 7. So another 0 here. Sorry, this 1 should have been a 0. That's what we were looking at. The rest of these squares are all filled with 1s. Now the question is, what would I actually put on the don't cares so that we get maximal simplification? Once again, 1, 1. Let's fill this up. Now you must notice that these 2 1s can be extended to a 8 block simply by making all these don't cares 1s. So once again, making all the don't cares 1s actually help. You have one block of 8, which is of course nothing but A. And not only that, you have another block of 4, which also uses these 2 don't cares. Now this block of 4 is in C out of D. This is CD bar. Now we have to take other straggling ones also into account. This one, I will join them with this one to get a 2 block. You should be able to easily convince yourself, but that is not the best that you can do, because these 2 1s can also be paired with these 2 1s to get a 4 block. And remember, our philosophy is higher the number of squares you can put in a block, the better. Now this 4 block, these 2 1s and these 2 1s taken together are each in C and they're all out of B. So these are C, P bar. Finally, these 2 1s sitting here, well, to get the simplest expression, what you need to do is put them as part of this 4 block. And that 4 block is entirely in B and entirely out of C. So it's plus BC bar. So that's the expression which will work for segment number G. I would urge you to work out the expression via the Karnaugh map technique for each of the other 5 segments in the 7 segment display that we have not done so far. In the process, you will see that unlike in our 2 examples, where making all the don't cares into ones was the best thing to do, there may be situations where some of these don't cares should be changed to 1 for maximal efficiency. Some others should be kept at 0. I am sure that once you get enough practice with the 7 segment display, it would actually show you how to handle any such problem with relative ease. And you will see that with enough practice, you can actually fill up the Karnaugh maps and find out the largest blocks and simplify the expression in almost no time at all. So in the next lecture, what we are going to do is we are going to take a look at what are called combinatorial circuits, combinatorial Boolean circuits or digital circuits, where we combine various gates to create useful circuits, which are actually building blocks of the modern digital computer. But that will be for the next lecture. Bye for now.